Today, we want to continue our work with double integrals, and today we're also going to upgrade to triple integrals, even though I haven't talked about triple integrals at all. We are going to apply the same strategy. The strategy is what's x between and what's y between for double integrals. For triple integrals, we're just going to add one more thing. What's z between? But for a warm-up, let's write two double integrals for the volume under the surface. F of xy is 9 minus x squared minus y squared, a circular paraboloid. And above the region R, which is going to be a quarter circle of radius 3 centered at the origin in quadrant 2. So we're going to look at where our circular paraboloid intersects the xy plane, but I only want the volume above this region in the second quadrant. And as usual, I want to set up two double integrals for this volume. So we're going to exploit the symmetry of this whole situation. So we're going to have one integral dy dx, and we're going to do another double integral for dx dy. So pause the video here, take a few minutes, and write these two double integrals. Welcome back to non-edited video. So what we need to do is describe this region R in such a way that our integrals will understand. We're going to use the same strategy that we used finding the area under a curve and above an interval. We're going to use the function as the height, and then the dy dx or dx dy is going to be the area. Then our strategy is to just write the double integral to tell the antiderivative the values we're going to plug into this expression. So let's take a look at a picture of the region with more detail on it. Here's a quarter circle of radius 3 in the second quadrant. Now, we know for this process that we're going to have to go the bottom and a top, and we're going to have to go and a left and a right. We can see that for the constant values of x in our dy dx integral, the left side is -3 and the right side is 0. The last integral always only gets constants. So for x, we're going to integrate from -3 to 0. It's not that big of a deal if you put these the wrong order. You start counting from 0 and go down to -3. Your volume will come out negative, and you'll be like, "Oh, why is my volume negative? It's a volume; it shouldn't be negative." Then you'll look at your integral and say, "Oh, I went from 0 to -3. I put the x's in backwards." And if you just switch the order, that'll just change the sign. So for the x's, for a typical x value, we're going to figure out what values of y we are between. So here's a typical x value, and we're just going to go straight up to from the bottom. The lowest y value is 0. So that's where our integral will start. And our highest y value is the circle, written y as a function of x. We know that this circle, x squared plus y squared equals 9. We can write y as two separate functions of x. Since we're in the second quadrant, y is positive, so I want the positive square root of 9 minus x squared. Any questions? Always start with the constants. That's because they have to be. Always start with the last integral because that has to be constants, and so that's easiest to figure out. What's x between? -3 and 0. What's y between? Now we have to figure out. We have to draw a line in the region, figure out what y is between. Let's go over to our dx dy integral. Our last integral here is the y integral, so we got to figure out what's y between, and that's got to be constants because it's the last integral. In this case, y goes from 0 at the bottom the 3 at the top. So we'll integrate from 0 to 3 dy. The x integral is where we're going to describe the curvy parts of our left boundary. So the x integral just goes from left to right. Now, in this case, going from left to right, we're not going to go all the way from -3 to 0. We're going to start at the curve, start at this quarter circle, and end at x equals 0. In this case, when we solve for x as a function of y, we want the left part of the circle. So we'll have the negative square root of 9 minus y squared. X is negative in the second quadrant. So I want the negative square root. Bottom to top, left to right. Or the other way around. Left to right, bottom to top. Any questions? This is why I picked the second quadrant where one of them was negative and one of them was positive. Could have also done the same thing by using the fourth quadrant because one of them is negative and the other one's positive. I wouldn't want to use the third quadrant because they'll both be negative. And we end up doing the same thing. Any questions? Now, in both of these cases, the integration is going to get a little bit messy. So notice notice I said write 2 double integrals for the volume. I didn't say find the volume, because now we'd have to calculate some double integrals, and these double integrals might get messy. Let's find out why. I know you're like, oh no, don't worry about it. We'll just take your word for it. We don't want to do messy integrals. Now, the integration parts, that's no trouble at the beginning. So let's take this first one here. The integration part isn't the hard part. We have the integral from -3 to 0 of the antiderivative of 9 minus x squared minus y squared dy. No problem here. It's just a polynomial. That's why I picked a circular paraboloid. So we're going to have 9y. The integral of 9 with respect to y is 9y. The integral of x squared, that's a constant term with respect to y. So it's going to be x squared y. Minus y squared. The integral of y squared with respect to y is minus 1/3 y cubed. And then we have to evaluate this as y goes from 0 to square root of 9 minus x squared. After we've done that, then we'll have to integrate dx from -3 to 0. So notice that I still have one of my integrals running around. Some of you may see already that you don't like where this is headed. Some of you don't like where it is right now. And some of you are like, oh, it's fine right now, and I don't see a problem where this is headed. But some of you already see the trig substitution showing up. So now we have to plug in the endpoints. Thankfully, y equals 0 is going to zero out all the terms. So I only care about plugging in the square root. So I'll have 9 times the square root of 9 minus x squared. Minus x squared times the square root of 9 minus x squared. minus a third of the square root of 9 minus x squared cubed. So minus 0. All three terms zero out when we plug in the 0. So right now you're looking at this and saying, well, this doesn't look too bad, but I haven't written down everything what we need to write down, because this is what we're integrating dx from -3 to 0. Just based on past history, Cal 2 and 3 students are generally sad when trigonometric substitution shows up. I don't really understand this viewpoint. I think this is awesome, knowing that we're going to be integrating stuff and having all this stuff being round and not using polar coordinates. I'm like, oh, awesome. This is going to lead to some trigonometric substitution. I can't wait. But students generally are like, oh, ew, no, trig sub. My favorite is once we learn about polar coordinates and cylindrical coordinates, students are still going to force themselves to do trigonometric substitution. So I think secretly, everybody loves trigonometric substitution. Because when I put this problem on the final, no one converts it to polar coordinates or cylindrical coordinates. And it's very funny. And it's like, oh, trig sub. Now you might be thinking, why don't we just use a machine to do the trigonometric substitution? It's like, well, the reason that we're not going to use a machine to do the trigonometric substitution is because if we're going to use a machine, back up a few steps and use the machine on the double integral. It's just going to block out a number anyway. If you're going to use a machine, don't use it in the middle. Just use it from the start. There's got to be a machine out there that can calculate your double integrals for you, like Wolfram Alpha. So unfortunately for our students, we're not going to do the fun parts. So prosecution stipulates students have done trigonometric substitution before and given enough time and motivation would successfully be able to calculate this integral. Any questions? At least these three terms are actual trig sub problems, not like the fake trig sub problems. Like sometimes you see a trig sub problem and the teacher wants to do the trig substitution, but they don't want you to work too hard on the products of powers of trig functions. And so they give you like x times the square root of 9 minus x squared, which is just a substitution problem, but they force you to do trigonometric substitution on it, which is just weird. Part of the reason that trig sub is such a pain in the butt is not the opening of trig sub and the closing of trig sub. It's the part in the middle where you have to integrate a product of power of trig functions that's either an even power of cosines without sines, or actually that one's good because you could just do the double angle identities, or an odd power of secants without tangents, and that one is messy. Any questions? Yes. The TI-84 will not be able to double integral. you're going to need a better machine. But you don't have to double integral if you only have a TI-84, then you do have to go this far, because note we do have just a single integral here. So now we just have to communicate this to our TI-84 and then hit enter and then wait and wait and wait, because your calculator will struggle with this. So if you want to do the double integral from, so I guess if you do just have the TI-84, you're going to do this classic style from the 90s, then you have to get this down to a single integral to communicate with your TI-84. Then you can grab your Wolfram Alpha and bring it up to the year 2000. I suppose you probably could write a program on your TI-84 that could calculate this, because it's just doing two different integrals. And one thing you can do on a TI-84 is program it to do the integral of an integral. I don't know if that it would be worth that much effort, because I think that would freak your TI-84 out. Oh, what are you asking me to do? Like, you can graph integrals and derivatives on your TI-84, because you just calculate the numeric integral of y1 with respect to x from, say, 0 to x. You should try it sometime and just watch how slow your calculator adjusts it. It's like a bloop, bloop. It's like seriously like a whole second between pixels. It takes a while. Oh, this is so much work. Any questions? Same thing happens on the other one, so don't think you could switch over to this other one and get around it because of symmetry. Okay. So what we want to do next is write a triple integral for each of these. Now I realize that we haven't discussed triple integrals, but we're just adapting old strategies. That's all we're doing. This whole double integral business was just taking our single integral business and just say, instead of saying x is between a and b, we're saying x is between a and b, and y is between c and d. And so here we're just going to add one more thing. What's z between? So we're going to be describing the solid in the integral, and then just integrate the unitless function 1. X went between, let's say, negative, I'm going to use this one, -3 and 0. Y was between 0 and positive square root of 9 minus x squared. Now, if we think about what the when we integrated the function, that was just the height. We used the circular paraboloid for the height. And what was the floor? So we'll use the circular paraboloid for the ceiling. And what was the floor? the floor was just the XY plane. So we're going to integrate Z from 0 to our function. Last time I cleaned this thing, I think I did a very bad job. So Z equals 0 is describing the floor. That's the XY plane above that region in the XY plane. The Z value of everything on that region was 0 because it's on the XY plane. And the ceiling was the function. How do you spell ceiling? Is it C-E-I? C-I, C-E-I-L-I-N-G, right? I know a ceiling and a roof are not the same thing, but our surface is infinitely thin. So the ceiling and the roof kind of are the same thing. It's not, the roof is no farther away than the ceiling is. So I'm just gonna cheat. I think you're right. I think I'm CEI. It's one of those words that looks wrong whenever I write it, no matter what. So CIE looks wrong and CEI looks wrong. So I'm like, roof. Now here's a triple integral. We're going to integrate the unitless function 1 because we're trying to find a volume, and our volume is going to be our height dz, our width dy, and our length dx. We could write another triple integral that goes dz, dx, dy, and that would just switch these two like we had on the previous page. But right now, I wouldn't want to write dz somewhere other than first. Let's just stick to these two. With 3 things, dx, dy, and dz, there's 6 ways we can set those up. So there's 6 permutations of 3 things. Any questions? I before E except after C. Oh, that one actually fits because it's like literally a C. Awesome. I always forget that because there's all the exceptions too. So we could also just adapt our previous one. Now notice the first thing that happens when we integrate this function. We integrate this 1, we get Z, and then we plug in the endpoints. Our function, 9 minus x squared minus y squared minus 0. So it works out. With the first step that happens, this becomes our double integral. Our first integration, dz, gets us our double integral. So when we integrate dz, we end up with z evaluated from 0 to 9 minus x squared minus y squared. And then the rest is our double integral. The important thing is not this particular problem. The important thing is the strategy. What's x between? Or sorry, what's x between? What's y between? What's z between? Any questions? This is going to work even if we start switching our coordinate systems. So if instead of using rectangular coordinates like we are here, even though so much of this stuff is just round, and we switch to, say, cylindrical coordinates would be more convenient for this particular volume, we're still going to be asking the same questions. What's r between? What's theta between? What's z between? Same set of questions, with one additional complication. Next thing would be to go back and write a simple integral for the volume, single integral for the volume. Technically, we already have one. But for this, you could think of maybe try a solid of revolution. You might want to avoid the trigonometric substitution, so you could try doing a solid of revolution. That's what's going to happen if you do the trig substitution anyway. But if you're like, oh, I don't want to do trigonometric substitution, I did not find it fun, even though all these ones would just be the same sign case, just x equals 3 sine theta. As soon as I go, I don't want to do trigonometric substitution. It's going to be a bunch of even powers of cosine. Any questions? Comments? Snide remarks? All right, that's going to do it for today. I'll see y'all on tomorrow, but have a good day and thanks for playing.